AMC10 now. So, today we're going to be going over number theory, so specifically, like bases, and don't worry if you already know like some of this, because we'll be going to some stuff that's pretty interesting. Okay. Okay. So let's go. So everyone knows base 10, I hope. Even if you never heard of the concept of bases before, you at least know that like this number, I just gave you an arbitrary number and you know what it means, right? It means 6,401, which means that there are 6 thousands, which is 6 times 10 cubed. And then there are 400s, which is 4 times 10 squared. And then there's a 1, which is 1 times 10 to the 0. And you know that this 0 means that there's 0 of 10 to the first. And you know, some older cultures, they didn't have the concept of 0 at first. So then they're just writing their numbers blindly, like 6, 4, 1. And then they just didn't put anything there. They were like, I'll let people figure it out themselves. So I think our number system is very good. And if you didn't know, it's because we have 10 fingers, right? So that's why every time you go one to the left, then the value of it increases by 1. I mean, increases by 10. Okay. So as you can see in base 10, each place value is 10 times the place value to the left of it. But like I said, this is from 10 fingers. What if we didn't have 10 fingers? Or what if we just decided to count differently? So there were some other like ancient people, I think the Aztecs or Mayans or something, they used base 20. And then the Babylonians used base 60. And we'll like talk about that today. So you can see that these numbers, even though they're still 6401, they're not base 10 anymore, right? Because you know that because there's a little subscript now, which tells you what base it's actually in. So in base 10, we saw that this one was worth 1 times 10 to the 0. This one worth, in base 10, we saw it was, oh my god, get that, 1 times 10 to the 0, and then 0 times 10 to the first. Okay. And then 4 times 10 squared, and 6 times 10 cubed. But if we look over here, this one is base 7. So we're gonna like take this example up here and just transfer it, right? So what this number means is 1 times 7 to the 0, and then 0 times 7 to the first, and then 4 times 7 squared, and then 6 times 7 cubed. So it's literally the same thing as we did over there, except every 10 is now a 7. So then we know that this number has a value of 6 times 7 cubed plus 4 times 7 squared, and then plus 1. This is literally just what bases mean. Okay. And you could evaluate that. And I'm not really sure what that evaluates to, so I'm going to use a calculator real fast. If anyone knows, please tell me. Okay. My calculator says it's 2255, which is a cool number, I think. So now, we use base 7, but now we have another example, which is base 12. And the thing about bases is you can have bases with numbers greater than 10 and less than 10. And I'll show you the specifics of the ones greater than 10 like in a few moments. But for now, let's like do the same thing, okay? So this is going to be equal to 6 times 12 cubed, and then 4 times 12 squared, and then just 1. So let's calculate that again. Okay, and this one is 10945. Okay, and I want you to notice that even though we started with the same number, right? It looks the same. It's 6401 base 7 and 6401 base 12. But in the end, this number was a lot greater when we converted them to base 10. And we can just put the little 10 subscript there, even though it's not necessary. And the reason why 6,401 base 12 is so much greater is because each place value has a lot more weight than it did when it was 7, right? Because now we're doing times 12 cubed instead of times 7 cubed. And 12 cubed is 1728. Well, 7 cubed is just 343. So it's like 6 times bigger. Okay. And then this last one, don't worry, it's getting kind of tedious, so we're not going to do it again. I just want to show y'all that this last one is actually not a real number. Because you may have noticed in base 10, we have the digits 0 through 9. Which means that once you get to the number 10 itself, you actually have to go to the next place value. You don't have a single character to signify 10. 10, the number 10 actually just means 1 times 10 plus 0. But there's no complete like number. There's no like special character for the number 10 besides combining 2 digits together. Okay, it actually only goes up to 9. So in bases, you're only allowed to use digits that start from 0 and go up to 1 less than the base you're in. So that means if we use base 4, we can only use the digits 0, 1, 2, and 3. Okay, so just keep that in mind for now. Does anyone have any questions so far? Okay. Oh no. Okay. So now let's go to the next page. So on the previous slide, I showed y'all a little bit of how to convert from something not in base 10 to something in base 10. But as you saw, it was kind of tedious, right? We had to evaluate all these powers and everything, and that's just really annoying. So instead, what we're going to do is I'm going to show you all a different way to convert. And you might think this one is a little bit easier, or you might not. It doesn't really matter. So we see this is base 16, and we also see a random E over there. And E is not a digit, obviously. But remember how on the previous slide I said we can use digits up to one less than the previous than the base we're in. So since we're in base 16, that means we should have digits. We should have digits for 0, 1, 2, all the way to 15. But the 15 has to be a single digit. So that's why after 9, we introduce like capital letters to signify digits. So the digits base 16 are going to be 3 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then A, which has the same value as 10. And then B, which has the same value as 11. C, which has the same value as 12. D, which has the same value as 13. E, which has the same value as 14. And F, which has the same value as 15. Okay. So usually the highest base that they'll ask is up to 16. So usually we only go to F. And I don't really know what happens if you run out of letters, because yeah, I've been sheltered and that's never happened to me before. Okay, so now let's worry about how to convert. Okay, so this time we're gonna start from the left, and then we're just gonna do a lot of multiplication. Okay, so we start with a 7, so let's just write a 7. And then we have a E to the right of that. So anytime we have something to the right, we're gonna multiply by our base and then add the digit to the right. So this E says we're gonna multiply by 16 and then add E, which is 14. Okay, and that is a big number. That's 126, apparently. Okay. And then, so now we've addressed the first 2 digits, but we still have another thing to the right of that, which is this other 7. And since it's the right, again, we're going to multiply by 16 and then add the 7. So now it's 2023, which is coincidentally our year. Or I don't know if you think that's a coincidence or not. It might be. Okay. So now, can y'all? Okay. Wait. I'll give this one. I'll do this one as well. So 5620 base 7. We're gonna start from the left. And I think this one might be slightly easier for you to understand this trick because the numbers are way smaller. So we have the 5. And then we're gonna include the 6. So we have to times 7 and then plus 6. And that gives us 41, I hope. Okay, so now we have the 6. And now we need to include the 2. So we're gonna times 7 plus 2. So this gives us 289. Okay, and then we have the 0. And with the 0, all we need to do is times 7. So this gives us 2023. Oh my God, it's the year again. That's such a coincidence, right? Okay, so um can y'all try the third one as well? Or do you have any guesses on what it might be? Okay. This is slightly depressing. No one has said 2023. Okay, so we're gonna go through this. I guess we could use like this long like multiplication method, right? But I feel like there's so many numbers here, and that's slightly tedious. So we're gonna go through the same way that we did on the previous slide. So we'll write it like this. This is gonna be 2 to the 0th, and this is gonna be 2 to the 1st. We're just writing out the values of every place value right now, and it increases from right to left. So 2 squared, 2 to the 4th, 2, oh, oops, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th, and 2 to the 10th. So this means this long number is going to be 2 to the 10th plus 2 to the 9th plus 2 to the 8th plus 2 to the 7th plus 2 to the 6th plus 2 to the 5th plus 2 cubed. And then, if I'm not wrong, this is going to be 2024 because I was waiting for someone to say 2023 and no one did. So that's really sad. But like these are just the ways that you're gonna be converting most of the time. So asking if you have any questions. And also, I guess something you should know is the most common bases are gonna be 2, 3, 4, and 16. And obviously 10, because we assume every number is in base 10. And this is called binary, ternary, I think. This is decimal, hexadecimal, and then I think 8 is like octal. So we use hexadecimal for like colors, and then computers think in binary, right? Because they're super dumb. They can only see like zeros and ones. But we can see more than that. We can hold 10 different characters, symbols in our heads. That's why we use decimal. Okay. So now that we know how to transform things into base 10, obviously we want to undo that because we realize that base 6 or something is so much cooler. So now we're going to learn how to transform out of those bases. And it's really just going to be a lot of division, long division. So We have 447, and we're gonna divide by 6 because we're trying to convert to the base 6. So we divide, and this is gonna give us 27. It's gonna give us 73 remainder 3. So we're gonna take this remainder and we're just gonna write it over here, aligned to the right. So we're gonna add things to the left. And then we have this 73, and let's just divide it again. So 73 divided by 6, that's 12 remainder 1. So we're gonna have a 1 because we write down the remainder, and then we'll take the quotient. But from this 12, you can see that it's gonna be, if you divide it, it's gonna be 2 remainder 0. So you'll write down the 0 as a remainder, and then you have a quotient that's less than 6. So it's gonna just be 0 remainder 2 if you divide it anymore. So you just write the 2, and then that's it. So 447 base 10 is actually 13 base 6. And as you will notice, when you're converting to these smaller bases, the number it ends out as is much bigger because they need like more to accommodate for the size, right? Okay. So let's do something similar for base 7. Okay. Which is, we're gonna do our division. So 447 divided by 7 is gonna be 63 remainder 2, right? Oh no, it's not remainder 2. Remainder 6. So we'll write down that 6 and then continue our division. So 63 divided by 7 is 9. Remainder 0. So we'll write down the 0 and then do 9 divided by 7 is 1 remainder 2. So we'll just copy down that 1 and that 2. So now we know that 447 base 10 is actually 1206 base 7. So you'll notice that the 1206 looks so much smaller than the 2013, even though they both represent the same value. Okay. Oh, so I wanted to show you something different for 246 to base 3, right? So you might have memorized your powers of 3. It's okay if you haven't, but like you'll get it through continued usage. So you might know that the powers of 3 go like 1, 3, 9, 27, 81, 243. And then you look at 243 and you're like, oh my gosh, that's so close to 246. So you can actually use this to your advantage, so you don't have to do such long division, because you can already see that there's so many steps in long division. It's really, really long. So you're just gonna use what you know about the place values and just write down the number. So you know that 246 is gonna be equal to 3 to the 5th plus 3 to the 1st. So you're gonna write down this number and put the ones where they're necessary. So we need a 1 in the 3 to the 1st place 3 to the 1st place value. So there must be a 0 in the 3 to the 0th place value, and a 0 in the 3 to the 2nd place value, and a 0 in the 3 to the 3rd place value, and a 0 in the 3 to the 4th place value, But in the 3 to the 5th place value, there's another 1 because we need that to add to 246. So that means our answer is just directly 100010 base 3. And that's 246 base 10. Okay. Does anyone have any questions? Okay, cool. So now that we know how bases work, we're gonna literally start from the very beginning of your math education all over again. And we're going to learn how to count. Even though we learned counting on probability on Friday, we're gonna do counting again. There's like never enough counting. So in base 10, you count normally, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I hope you already know how to do that. So what you might have noticed, or like what I spoke about before, is when you get to 9, you write down 1 0 for 10. Which is actually 1 times 10 to the 1 and 0 times 10 to the 0. And then from then onwards, you keep increasing the units digit until you have to carry again. So at 19, it goes to 20. And then at 29, it goes to 30. So now let's consider base 3. And as a reminder, this is called ternary, I think. Here, we only have the digits 0, 1, and 2. Which means that once we run out of digits, we have to carry. Just like in addition, you have to carry if you get a sum greater than 9. So we have 1, 2, and then our way to write 3 is going to be 1 0. So because this is going to be 1 times 3 to the 1 plus 0 times 3 to the 0. And then once we get to 10, we can continue adding 1 to the units digit. So 11, 12, and then now we can't write 13 because there's no such thing as 3. So we have to carry again. So now it becomes 20 because this is 2 times 3 to the 1, and then 0 times 3 to the 0. Okay, and then we go 21, 22. And now we have a dilemma because there's no such thing as 3, right? So we have to carry. But then this thing, there's also no such thing as 3. So then we carry again, and it gives us a 100, which means 1 times 3 squared, and then 0 times 3 to the 1, and 0 times 3 to the 0. So this is 9. And we're already at 100 on our 9th number. Okay, and then after that, we continue like normal, right? So 10, this is 10, and that's 11, if we're considering base 10. Okay. So hopefully y'all all know how to count now. Because we're moving up in grade levels. We're going now to like first grade, kindergarten. I don't know. And I have a distinct memory of learning addition tables with reflex math, but I think y'all are using like Prodigy or something like that. Well, okay. So now we're going to addition, where addition is like repeated counting, right? So if we have 3 and then we add 4, we just count 4 more. then 3. And then we realize that it's 7, right? Because 7, 3, and then go. 4, 5, 6, 7. And we added 4. Okay. I hope y'all all knew what addition was the whole time. So there's an addition table base 10, which is like we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can like to add numbers, we look at the row for one number and the column for one number. So it's like 3 plus 8 equals 11. And I'm sure you know how to do that. But we can create our own addition tables based any number, right? So let's say we wanted to do addition base 5. So we have the possible numbers 0, 1, 2, 3, 4, and that's it. 0, 1, 2, 3, 4. Okay, so obviously 0 plus anything is going to be the same number. And then if we add 1 to each number, it's going to be 1 more. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. But then when we get to 4 plus 1, we don't have the number 5, which means that we'll have to carry. So just like how 7 plus 3 over here, it carried to become a 10, we're going to have to carry and also become a 10. Because as a reminder, 10 base 5 is equal to 5. I guess you'll just go home and tell your parents that you learned that 1 plus 4 is 10 today. Okay, so let's continue. This is going to be 3, 4, and then we have a 2 plus 3. And oh no, that's bigger than 4. So that means we'll have to carry and write down 10. And then 4 plus 2. Oh, that's 11. Okay, so 4, 10, 11, 10, 11. And then 3 plus 4, that's 7. But 7 base 5 is actually going to be 12. 3 plus 4, yeah. And then 4 plus 4, that would be 8 if we consider base 10. But if we convert that to base 5, it's actually 13. So now that you have this super handy addition chart, you can do like addition with base numbers without ever having to convert them back to base 10. So let's say you wanted to do like something super long, like 3, 0, 2, 3, 1 plus 2, 2, 4, 4, 2. So you can just add them column by column, just like you do for addition. So the 1 plus 2 is 3, and then 3 plus 4, that would be 7. And that's equal to 12. So we're going to write down the 2 and carry the 1, because as we see here, 3 plus 4 is 12. So 2 and carry the 1. And then we do 1 plus 2 plus 4, and this is going to give us 12 or 7 again, which is equal to 12. So we're going to write down the 2 and carry the 1. And then 1 plus 0 plus 3. 1 plus 0 plus 2 equals 3. And 3 plus 2 is 10. So our answer for 3, 0, 2, 3, 1 base 5 plus 2, 2, 4, 4, 2 base 5 is 1, 0, 3, 2, 2, 3 base 5. And we didn't even have to do any like gross conversion at all. Does that make sense to everyone? Okay, so now we're gonna do pretty much the same thing, but with multiplication. And so with multiplication, you're just gonna like think about the numbers in base 10 first, and then convert them into whatever base you're going for in your head. So let's use the base 5 example again. If you have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So obviously this part is easy. And then the multiplying by 1 is easy as well. Thank God for ones. Okay, so now 2 times 2 is 4. And then 2 times 3 is 6, which is 11. And then 2 times 4 is 8, which is 13. And then 11, 13, we can just fill those in. So then 3 times 3 is 9, which is 14. And then 3 times 4 is 12, which is 22. And then 3 times 4 is 12. Oh, right. And then 4 times 4 is 16, so that's 31. So here is our multiplication table, base 5. And again, you can do your normal multiplication and division. So, oh, well, not division actually. So for multiplication, we can do like 341 times 3. And this is all base 5. So we do that. We write the 3, and then we do 4 times 3 is 12, but that's equal to 22 base 5. So write down the 2 and carry the 2. And then 3 times 3 is 9, plus that 2 is 11, and that's 21. So this is 21, 23 base 5. And this is actually the one thing that was not intentionally close to 2023, but it's good that it turned out that way. So then the problem with division is the same problem as with like normal long division, as in you have to know the multiples of everything you're dividing by, of that like number you're dividing by. Like if you're doing like 500 divided by 23, you have to know all the multiples of 23. And that's already difficult in base 10, but doing it in different base is just tragic. So honestly, I'd recommend you just convert to base 10 and then do your division there. So that way you don't kill your brain. But like for anything else, you can do in other bases without much trouble. So does anyone have any questions? Okay, and something cool is that you'll always end up with a 2-digit number max if you're multiplying 2 digits together. Because even if you're doing like base 16 and we're doing f times f, which as a reminder is 15 times 15, it'll only end up as 225, while a 3-digit number in base 16 would be 16 squared equals 256. So you'll always end up with a 2-digit number, which means it's relatively easy to convert between 10 and that base. So you don't have to worry about like boggling your brain. Yeah. Okay. So now it's time for something that does not look like anything we've done so far, but will help us do super, super hard, amazing base problems. Okay. So, let's say we had this sequence of numbers, right? It starts from 1, and then every time it goes down, every time you half it, So it starts from 1 and then goes to half and then a fourth and then an eighth and then a 16th and on forever. And you want to add up all these numbers together, but like you don't know how to add up infinite numbers. Okay, this is slightly strange. So what you do instead is we have this trick, okay? And you're gonna see that this number, even though we're adding up infinite things, is not gonna equal infinity. Okay, so we're gonna take this thing and then I'll just like casually copy paste it because I don't want to write it over again. Oh my God, it worked. Okay, so also we're gonna double it. So 2s, where s is the sum that we want to find, is gonna be 2 plus, because we doubled the 1, and then we have the 1 from doubling the half, and then half from doubling a fourth, and fourth from doubling 1/8, and 1/8 from doubling 1/16, and 1/16 from doubling the invisible 1/32 that we didn't write. So now, if you look at these numbers, if you look at these sequences, they match up very well. Because if you look at it, the 2 became a 1. I mean, the 1 became a 2, and the half became a 1. So now there's a 1 in both of these sequences. And similarly, there's a half and a fourth and an eighth and a 16th and on. There's something for all of them, except for the 2 in front. It's kind of lonely. So that means we can actually, subtract the second sequence, the original one, from the first. And it'll give us, since everything cancels, whoosh, whoosh, whoosh. It'll give us s equals 2, which means that our sum actually equals 2. And if you were to evaluate this slowly, you'll see that it makes sense, right? Because it gets closer and closer to 2, because you start at 1, and then you go to 3/2, and then you go to, oh no, math is hard, 7/4. And then you go to 15/8 and 31/16 and onwards. But it gets really close to 2, but it just never seems to reach it. But now we've shown, if we do this infinite times, it does end up as 2. Okay, so that probably made no sense for why I'm teaching it now, but you'll see. It's super fun. Because now we're moving up in our math levels. We're maybe in like 5th grade now, and we know what decimals are now. So we have some decimals and we want to convert them to base 10. So obviously the front part is the same as always. It's going to be 64 plus 40 plus 3. So that's 107. And then the back part. Well, this one was 1 times 8 squared. And this part was 5 times 8. And this part was 5 times 8 to the 0. This one was 1. Oh, we have class tomorrow, and that's going to be the last one. So, as you know, in base 10, if you put something like 123.4, that means this is 4/10. And similarly, this 0.2 is 2 times 8 to the -1, which is the same thing as 2/8, or 2/8 to the 1. So, therefore, this 153.2 base 8 is going to be 107 plus 2/8. And this 2/8 can be simplified as 1/4. And you can write 1/4 as 0.25. So this 153.2 became 107.25 base 10. Okay, and now we have okay, so now we have this 222 ... And that means it's going to be repeating forever. So we're going to have 153.2 repeating. This bar over the 2 just means that it goes on forever, but I don't feel like writing it infinite times. It just goes on infinite times. Like, you might have seen this if you're doing 1/3, right? It's equal to 0.3333, and it just never ends. And we can shorten that by writing 0.3 repeating. So, let's do this. Okay, so we already found the 153 parts. That's equal to 107. And now we just need to figure out the 2 repeating part. So this is going to be 2/8, this part. And then it's going to be plus 2/8 squared. And then it's going to be 2/8 cubed. And on and on and on. And every step, it's going to be 2/8 to a higher power. Okay? So that's why we talked about adding these sequences on the previous slide. So let's look at this sequence. S equals 2/8 plus 2/8 squared plus 2/8 cubed, and on and on and on. Well, just like we multiplied by 2 the previous time, we can multiply by 8 here. So 8s equals 2 plus 2/8 plus 2/8 squared plus 2/8 cubed, and on and on and on. So now, just like last time, we can do our slick subtraction thing, and then it gives us just 7s equals 2. So now we have the s equals 2/7. So this 0.2 repeating base 8 is in reality just equal to 2/7. So 153.22 is going to be equal to 102 and 2/7. But if you wanted to write that as a decimal, you can write 1/7 as 0.142857 repeating, as in it repeats that value forever. And I just memorized that. And if you have higher fractions with the denominator 7, it'll just cycle these digits. So 2/7 is going to be 0.285714, and then repeating. And then 3/7 is going to be 0.428571 repeating. So it's just using these same digits in the same order, but choosing the next lowest number to start with. So a 153.2 repeating base 8 is the same thing as 107.285714 repeating base 10. And I guess you can choose whichever one you like more, base 8 or base 10. Okay. Hopefully that makes sense to everyone. Let me know if you have questions. Okay. I think this is our last slide. Good job, everyone. So I don't really remember what grade we learned fractions, but we finally unlocked fractions. Parts of a whole. Yay. Okay. So we're gonna start with some base 10 fractions, and then we're gonna use some base fractions that we want to write as decimals. So we have a 717 over 343. And so, oh my God, I just dropped my mouse. And then something you might notice is 343 equals 7 cubed. So that gives us very good vibes about this. Because if we didn't have the, okay, wait. Because if you were thinking in base 10, right? Then a 343 is basically just a 717 over 1000. And that's so easy. All you need to do is move the decimal places 3 to the left. So we can apply the same principle here. So first we're going to convert 717 to base 7. And 717 base 10 is 2043 base 7. And then we're dividing by 343. And 343 base 10 equals 1000 base 7. So now, just like in base 10, we're dividing by a bunch of zeros. A 1 with a bunch of zeros. So all we need to do is take this decimal point, move it 3 spaces to the left. So 1, 2, 3, and it's going to go right here. So that means 717 over 343 base 10 is 2.043 base 7. And that was so nice and easy. That's so awesome. Okay, so now we have 1/8. And unfortunately, this does not look like a power of 9. I don't think 8 is any power of 9. So it's going to be slightly harder. But we can do something, okay? So okay. Let's see if I can finish. So if we took a sequence, remember previously we did 1 plus 1 over 2 plus 1 over 4 equals 2. And then so this is called a geometric sequence, where the first term is a, and then every subsequent term is ar squared, etc., where r is the common ratio. So here a equals 1 and r equals 1 over 2. So then the sum of this sequence, because of the method we did it, where we multiplied by 2 and subtracted, it always has a formula, which is gonna be a over 1 minus r. So for example, here that's 1 over 1 minus 1 over 2, which is 2. Just like we calculated. And similarly for the other one we did, 2 over 8 plus 2 over 8 squared plus 2 over 8 cubed. Using this formula, it's 2 over 8 over 1 minus 1 over 8, because that's our common ratio. Every time we multiply by 1 over 8. So it's going to be 2 over 8 over 7 over 8. So that's 2 over 7, and that's our sum. So here, you might have noticed that like this denominator is exactly 1 less than the 8. So here we suspect that that 1/8 is just some geometric series thing in with 9. So for example, if you were to try 1/9 plus 1/9 squared plus 1/9 cubed, etc., it would be 1/9 over 1 minus 1/9. So this is 1/9 over 8/9 equals 1/8. So we got our 1/8 that we wanted, but what exactly is 1/9 plus 1/9 squared plus 1/9 cubed, etc. in base 9? That's actually just 0.1 for the 1/9, and then 1 for the 1/9 squared, and then 1 for the 1/9 cubed, and on and on and on. So it's gonna be 0.1 repeating, base 9. Yay. Okay, and now for the last question. So in base 10, we have like that repeating thing, right? And something you might notice is if you convert the repeating thing, for example, 0.2 repeating, and this is base 10, to a fraction, it's going to end up as 2/9. And if you converted like 0.23 repeating, which is 0.232323, like the whole thing under the bar reboots, then it would be 23/99. So what's happening is you just copy the number under the bar and then divide it by 9 for how many 9s are under the bar, or for how many numbers are under the bar. So then we can apply the same logic to our base 7 thing, because in base 7 our version of 99 is actually 66, because there's nothing, because once we get over 66, then it goes straight to 100. So basically we want to convert this fraction into something with denominator 66 in order to write it base 7. And obviously the denominator currently is half of 66. So we can just double the numerator and denominator. So 5 times 2 is 13, base 7. And then the denominator is going to be 66. So 5/33, base 7, is the same thing as 13/66, base 7. So that's just going to be 0.13 repeating, base 7. And that is our answer. Okay. Yeah, that's the end of class. Thank you for coming, guys. Have fun with Daniel.